All right, let's get started. So welcome back to another video session on the symmetrical component, right? We're starting with the new chapter. What do we, why do we have to learn symmetrical component, right? I think the symmetrical component is very important to analyze the unbalanced fault, okay? Let me clarify to you, right, what kind of fault that we have discussed in this course. Okay, we have the so-called we have learned in the last chapter about the balance fault or three-phase fault. Another name would be a symmetrical fault. Okay, symmetrical fault due to, why do we use the term symmetrical? Because the topology of the fault is symmetry. Okay, you can, when we have the symmetrical fault, we see that the disturbance that the phase A, B, and C experiences, right? I mean, the phase A, B, C has the same kind of disturbance or the short circuit to the ground. Okay, the three-phase fault, if we have, gather the statistics or the number of occurrence, so the total number of three-phase fault is less than 5%, so it's rarely happen. Okay, this is the key. This is rarely happen. Okay, this is rarely happen. Um, The types of fault that normally occur in power systems is the unbalanced fault. So basically, the unbalanced fault is the fault that the disturbance of the three phase is not the same. Okay, so we can see from the picture on the right side that the first type of unbalanced fault would be single line to ground. So you can see that in this case, just only the line C got the disturbance or short circuit to the ground, while phase A and B are still running at the normal operating condition. So there's still power flow from source to load. Okay, so in this case, the fault just happened to phase C only. So you can, that's why we call single, right? Single phase to single line, just one line, short circuit to the ground. So the statistics of this kind of fault, it's about 60 to 75% of the total number of occurrence. So mostly the types of fault that happen to the power system is a single line to ground. Okay, double line to ground, you can see that the name suggests double line, so there are two lines that have the short circuit to the ground. Okay, in this case, that are phase B and C, right? And the phase A is still running at the same, the normal operation. So the number of occurrence is less than single line to ground. Okay, it's about 15 to 25%. The last type of unbalanced fault is line to line. You can see that this is a short circuit between the two lines. Okay, the short circuit is in between the two lines. Line means the carrying conductor, right? The current carrying conductor. So these are the short circuit between these two. Okay, so the percentage of occurrence is less, as is the least among unbalanced faults. So it's about 5 to 15%. So why are we interested in learning the symmetrical component? Because the symmetrical component here will be the tools to analyze the unbalanced voltage and currents. Okay. We have learned from several courses in basic power system is that the main assumption that we have made in learning three-phase power system is that the three-phase are balanced, right? Most of the times that we talk about the three-phase, so we assume that the system is running in balanced condition. In balanced condition, that's why we could analyze in per phase, right? We could, when we want to analyze a circuit, we normally use the per phase analysis. Okay, that was an assumption that we usually use. Okay, but what happened if the system, you can see that we have this kind of fault. So the operation of the power system is no longer balanced. So when there is no longer balance, you can't use the per phase analysis. So the symmetrical component, okay, is the tool to deal with such an unbalanced condition. Okay, so the symmetrical component will try uh, to transform, right? Basically, I would try to use the term we use the symmetrical component to transform unbalanced, right, system into, right, virtually balanced system. You understand what I mean by virtually, okay? We were trying to transform the unbalanced system, and we are trying to deal with the system which is balanced. So the power engineer, as I said several times, that the power engineer love to simplify things. Okay, that's why we have invented the symmetrical component concept, to transform the unbalanced three-phase voltages into balanced, okay, voltage and current. But of course, you can't directly transform the balance into unbalanced to balance. Okay, it would come with some price to pay. So in this case, when we transform the three-phase voltages, we will have to deal with the so-called zero, positive, and negative sequence voltage. Okay, so basically, we try to transform unbalanced to three types of sequences. Okay, three sequences in balance. So you will see in this video, right, how to transform this and what are the benefits of applying symmetrical component. Okay, now you can see from this picture, okay, we are discussing the unbalanced three phase. You can see that in this phasor diagram, okay, the VA, VB, and VCs are of course unbalanced. Why can I say this is unbalanced? Because because of two properties. Okay, the length of this voltage, okay, the length of these three voltages are not equal. Okay, and the first thing is that the magnitude of this is different. The magnitude is different. Okay, this is the magnitude of VA is not equal to VB, it's not equal to VC in terms of the magnitude, right? Or it could be, I would add absolute for the sake of clarity. Okay, and the second thing is that the phase angle separation. Okay, the phase angle separation is not, right, 120. So this is these are the two conditions that made the voltage unbalanced. So the phase angle separation is not 120. So this is not balanced, of course. Okay. The concept of a symmetrical component is that we are trying to express the VA, VB, VC as a sum of voltage vector 0, 1, and 2, that this 0 would represent by the zero sequence, okay, and 1 is positive sequence, and 2 is negative sequence. Okay, so these are the two sequences that we mean. So we will try to express VA, VB, VC in terms of VA 0, VA 1, VA 2, for instance. Okay. Now this is the picture of the phasor A, B, and C. You can see this is VA, VB, and VC. We are trying to express VA as a sum of the vector between the component of component 1, 2, and the component 0. Okay, can you see this one? VA expressed in terms VA1, VA2, and VA0. Let's take a look at VB. Okay, if you look at VB, VB, you can also express this in terms of positive, negative, and zero sequence, the sum of these three components. Similarly, for VC, right, you could express this in terms of V1, positive, V2, right, negative, and V0, zero sequence. Okay, so let us see the property of each of the component 1, 2, and 0. Okay. Now I will try to highlight this to you to make this clear in just one slide. Okay. Now you see from the for example this V1, right? You can see that the V1 here, VA1, VB1, and VC1. What are the property of when we compare just the positive sequence? You can see that for VA1, VB1, and VC1, the length of these arms are equal. Okay, the lengths of these are equal. Okay, VA, VB, VC in positive sequence, and the phase angle here, the phase separation, is 120, 120, 120, and 120. Okay, and if you can see from here, okay, the positive sequence, meaning that you stand at the zero reference, right, and we rotate the vector counterclockwise, then you see the A phase coming first, right, entering the goal first, following by B and followed by C. Okay, so the positive sequence, or with the subscription 1, right, positive sequence. The other name we call ABC sequence, ABC. Okay, we are standing at the goal in this case, and we rotate in the positive direction, which is the counterclockwise direction here. And you see the phase A, B, and C in sequence, in this sequence. Okay, that's why this is the ABC. Okay, ABC. That is used in by that is denoted by the subscript 1. Okay, so let us delete the positive sequence. Okay, in this case, you see what we mean by positive sequence. When the negative sequence, negative, okay, I will change the color, maybe in purple. Okay, V2 negative sequence. So the negative you see from the subscript 2, subscription 2 to VB2. Where is VB2? Is here, right here. Okay, and VC2. Okay, if you see these three vectors, right, you can see that let me draw this vector here. You will see the VC is point down here. Okay, and VC2, VA2, and VB2 is pointing in this direction. So this is VB2, okay, from this picture. If you rotate this, in the same idea, we rotate this counterclockwise and we stand at this goal, right? You can see that the phase A just enter the goal first, so the A first, followed by C, and it's followed by B, right? So the sequence that the phase voltage, right, just enter to the goal is in VCB sequence. So this sequence ACB is called negative sequence. Okay, next is called negative sequence, or ACB sequence, right? And this is the the negative sequence. So what do we understand by the zero sequence? Now the zero sequence you would see, right? The first one is simple, VB, VA, VB, and VC. Now you see that VA, VB, and VC are pointing in the same direction. Even but this is a rough drawing. But in this is just approximation. So A, C, and B are in the same direction. Okay. So now we can just decompose this picture into the three components, right? The positive component is A, A1, VB, and VC, right? Or this is A, B, C sequence, okay? Whereby you have the negative sequence, we have A, C, and B, okay? This is A, C, B sequence. And the zero sequence is the sequence at which the angle separation is zero. Okay, that's why this is called a zero sequence. Okay, now you can see that with the unbalanced waveform, okay, with unbalanced phasor, A, B, and C unbalanced. Now you can express this unbalanced phasor in terms of three components of balanced phasors. Okay, these are the balance. So the balance means that okay, the length is the same. When we say balance means the length is the same, okay, and the angle separation between these faces are the same. In this case, the angle separation, the magnitude of the angle separation is 120. This is 120, and the angle separation here is 0 because it's parallel, right? So the concept of balance, right, would line into equal magnitude, right, for the phasor, equal magnitude and equal angle separation. Okay, either this angle separation can be 120 or 0. Okay, this is the definition. All right. So these are the explanation. All right. The zero sequence, we use the term zero phase displacement, or it can be a separation. Okay, positive it's either positive and negative could be plus or minus 120 and the equal magnitude. Okay, these I have already described. Now, this is the question, in order to transform the unbalanced phasor, VA, VB, and VC, we want to express this in terms of VA0, VA1, and VA2, VB, similarly, VB0, VB1, and VB2, VB2. Okay, for VC, we want to express in zero, positive, and negative sequence. So the question now is, sorry, what are those components? What are those three components for each of the three voltages? Okay, now you end up, you want to find VA0, VA1, VA2. We want to find these 9 variables, but these are impossible because, you have 3 equations, but you have 9 variables. So you have to reduce somehow, we have to reduce the number of variables, okay, by using some geometrical property. In this case, it is defined in terms of the A operator, which will be explained to you. Okay, now you see we have to group the zero sequence component, because this is all these three, right, with the subscript 0. We call this the zero sequence component, positive zero sequence component, and negative sequence component. We have to analyze the components of each of these 3 groups. Okay, now if we define the A operator in this case. Okay, the A operator is like a unit vector, right? This is a unit vector with the angle displacements of 120 degree. Now we define A is the unit vector of the magnitude 1 with the angle 120. Okay, if you have this 120, everybody knows that the A here is the it can be expressed in terms of rectangular coordinate with negative a half plus j square root 3 divided by 2, which is the A over here. 120 means that this is 60 degree. okay, 60 degree, and you can see that this lines in quadrant 2. Okay, that's why we have this is negative part plus the positive imaginary part. Okay, if you define this as a and the a square would become a and the angle of 240. Okay, you rotate this with another the angle of 120. Basically, you just rotate this counterclockwise. Okay, so this would line in the quadrant 3 with both negative real and imaginary parts. Okay, so these are the two operators that we use to transform this equation, right? And then we transform this to reduce the number of equations into from 9 to 3, basically, because we have just 3 equations, right? We will transform this equation into 3, okay? 3 variables, okay? If we analyze the positive sequence component, okay, the positive sequence component looks like this: VA here, VB here, and VC here. We express this VB and VC in terms of the A operator. So everybody knows that the VB here is the rotation from VA in the positive direction twice, right? Twice time. One time rotation results in 120 degree phase shift. You can see that VB in this case, you have to rotate 240 degree. So you have to multiply the VA, right, by A square in order to achieve VB in positive sequence. Okay, so VB here could be expressed in terms of A squared times VA. Okay, while the VC, right, VC would lies in this position. Okay, in order to get the VC from VA, you just rotate just once by the A operator. You just rotate counterclockwise just once. So you multiply VA by A operators in order to get the VC. Okay, now you can express VC and VB in terms of VA. Okay, so let me write in this line. Okay, you can see that your VA phasor of VA. Okay, it can be expressed in this form, right? You can express this format right here. You can express this column, positive sequence column. Okay, now you can have VA1, right? So VB, right? You can express your VB by what? A square VA1. Okay, while we see here the third line, you can express this in terms of A V1 VA1 plus. Okay, now you have reduced the number of the variables from VA1, VB1, VC1 in order to just VA1. Okay, you can have just one variable at in this column. Okay, you can have just VA1 in this column. Is it okay? Now let us continue with the negative sequence. The negative sequence, you see, not with negative sequence, it looks like this. So the VA, if you want to get the VB, right, you just rotate this by just once by the A operator. So VB just A times VB just A times VA. Okay, and from this point, if you want to get VC, right, you just rotate twice. Okay, so you multiply this by A square in order to get VC2 from VA2. Okay, this is clear. So for the zero sequence, right, everybody knows that the zero sequence, these 3 vectors are the same. So you just express just once. Okay, in this case, right, you can substitute the properties that we have derived earlier, right? You can reduce the number of variables from 9 to just 3. Okay, I have shown you already for this positive sequence term. right? For A, B, C, you can express this in terms of VA, right? VA times A squared, VA times A, and similarly, you can, you know, express the negative sequence, right? To get, in order to get VB, you just rotate once. In order to get VC in negative sequence, you just, rotate twice. Okay, so now you can reduce the three, equation, nine variables to just three. Now you can have this property. You can rewrite this equation in a matrix form like this. Okay, now you can see that the the VA, VB, VC can be expressed, in terms of the V0, V1, and V2. Okay, V0, V1, and V2. In this case, what we saw from this equation, just the magnitude, right? It's just the magnitude of this phasor, the magnitude of the phasor. Why are we interested just the magnitude? Because we know it already that for the positive sequence, right, the angle separation is in this form, right? VA in here, VB in here, right? If we see it's here, this is positive, right? Soon after you know the magnitude, there's no problem to find VB and VC, because the angle just shift by 240 or the negative 120, right? If you know just magnitude, you can define other variables. Okay, for V2 similarly, if you happen to know just the angle, the length of this face of this arm, the magnitude of the face, right? You know the angle straight away. So the zero sequence is not a problem, because the the zero sequence in each of the faces is the same, right? So this is the transformation from uh, right, VA, VB, VC. These are the original quantity. You can have this relationship, right, in terms of V0, V1, and V2. Okay, what are we interested is not like this, right? Because normally when we measure, VA, VB, and VC. Okay, this side. The unknown is in this part. This is unknown. Okay, so now, in order to know the unknowns, right, you just find the inverse of this and multiply this by on the both sides of the equation. Okay, in order to achieve that, we have to understand a little bit about the complex identity. Okay, complex identity. Now you see that if A is the operator with the magnitude of 1, then the angle of 120, right? You see this is it. This is A. You have seen that this is A. I'm sorry. This is A. Sorry, this is 1. This is A. This is A, because you have shifted this by 120. The angle, the length is 1, right? You rotate twice, you get A square. Okay, every time you put the power, you increase the power by 1, it will shift by 120. That's why if you rotate one more time, right, it will come back to the original position. In this original position, the vector is expressed in terms of 1, the angle of 0. This is clear, right? This is rotation by 3 times, right? This is the 1 time, 2 times, 3 times. 3 times you get at the same position. Once you rotate one more time, you get a to the fourth. Then you return back to a. Okay, and this is the identity, common identity. The sum of all these three vectors is 0. Okay, or sum of these three vectors is 0. Why is it so? I think this has been discussed several times, right? The sum of these two, right? Sum of 1 and a square. 1 plus a square is here, and you plus with the a. Okay, this vector is 1 plus a square, right? The same length with this guy. So 1 plus a square plus a, it becomes 0. Okay, Now, I think this is not the big issue, right? You can analyze this yourself by using the simple mathematics. 1 minus a, 1 minus a, minus a is 1 minus a is this way. So this is minus a. So 1 minus a is right here. This is 1 minus a. So everybody knows that this is an equilateral triangle with 1 1, and the angle here is 120. So this is becomes 30 and 30, right? The length of this vector, right, is square root 3 times, right? Square root 3 times of the arm of this guy, and the angle is negative, become negative 30. Okay, so you get this one. Okay, I would just leave this. You can play around with with this geometry, simple geometry, right? But these are the common property. So we use this common property, to find the inverse. Okay, we can see that, from the earlier formula, right? We express the VP, which is the phase quantity. These are called the vector. This vector is called VP, standing from the phase voltage. Okay, and in this case, we in this slice, right, we use the vector vs, which stands from the sequence voltage. Okay, so in short form, we see that the phase quantity or phase voltages can be expressed in terms of a matrix A times the vs. Vs is a sequence component, right? Sequence voltage. Okay, so as I said earlier, that we are not interested in this kind of expression, because we know this guy, and we want to know this guy. We want to solve for this guy. So we have to know the inverse, right? Using the mathematics, we have to play around with the inverse of this matrix. Okay, okay, we have to find the inverse of this guy. The inverse of this guy, A, how much is it? Okay, we have work on this. People have worked on this, so I'm not going to do in the detail, right? So the inverse of this is 1/3 of this matrix. Okay, 1/3 of this matrix. You have to compare. You should compare between A and the A inverse, right? You see that the first row and the first column remains 1. Okay, the way to memorize these things is the first row and the first column remains unchanged, right, which is 1 in this case. The change just in the rest part. Okay, in the rest part. Now the change is in this way. Okay, the change is just a swap of these two lines, you can see, right? This a square and a becomes on the third row, and a square turns to be in the second row. So the inverse is like this. So remember that if you deal with the inverse, right, if you want to find the sequence component, you have to deal with the inverse. And the inverse of the matrix, right, the matrix will be multiplied by 1/3. Okay, this is the inverse. Okay, now, this is the equation that we have to deal with, right? You know the VA, VB, VC, you know the V phase, right? And you want to find the V0, V1, V2. We want to know the how much is the sequence voltage. Okay, so basically you have to deal with solving these three equations, right? These three equations. It's the same equation, but this is written in the matrix form. This is written in three separate forms. Okay, this is a three separate forms. So now you can have you can draw some observation based on what we have learned earlier, right? You can see that if you apply, right, VA, VB, and VC, if VA, VB, and VC is balanced, okay, if VA, VB, and VC are balanced, what would happen? VA, VB, VC are balanced. You can see that VA plus VB We have learned that VA plus VB plus VC is 0. Okay, if balanced, you see it's already several times VA, VB, VC, right? This is positive sequence, right? The sum of these three vectors is 0. Okay, because VA plus VB is this guy here. Okay, this is VB, and this is VA plus VB, right? It's you cancel this guy. So this has become 0. You can see from the first equation that if the sum of these three vectors becomes 0, then this is 0. Your V0 is 0. Okay, so this leads to the first conclusion, right? If you deal with the balanced three-phase system, then there is no zero sequence. Okay, if you deal with balanced three-phase system, the zero sequence is 0. You don't need to analyze the zero sequence network. Okay, you don't need to analyze the sequence, the zero sequence component. All right, because the sum of this vector is 0. Okay, now you could also apply the transformation to not only just voltage but also the current. Okay, so the IP, the phase current and the sequence current can be expressed in the same fashion. IP, right, standing from the voltage vector of phase current. IA, IP, and IC. IS is a sequence current, right? I0, I1, I2, I0, I1, I2. Okay, you could also express in a certain fashion, and the same relationship pertains, right? Because you multiply this by the inverse on the both sides, then you find IS based on the known IP. Okay, and this is the similar expression as we showed it earlier, right? Now you could see that for the sequence current, okay, the one third, the coefficient one third, you know, tell us that this is the inverse, right? It comes from the inverse. So we can express I0, I1, I2 in terms of the phase quantities IA, IB, IC. Now again, if the three phases Y connected, right? If it is Y connected, the neutral current, okay, the neutral current is the three times of the zero sequence. Okay, why is it so? Because now you see if it is Y connection, okay, Y connection is like this, right? Then the neutral point, okay, neutral is a common point, okay, of the star or Y connection is phase A, B, and C, right? Normally we assume the current flowing into the neutral, okay, IC, right? And the neutral current just flow out neutral, right? Now you see that your IN is equal to IA plus IB plus IC, okay? Your neutral current is the sum of this. Okay, now you see that if you substitute this into this, so I0 becomes one third of IN, or your neutral current is three times of zero sequence. Okay, now this is the observation. So note that the neutral current just equal to three times of zero sequence current. Okay, if you want to know neutral current, okay, you can, if you manage to decompose the unbalanced current into zero sequence, right? Once you know the zero sequence current, the zero sequence current, you just multiply by 3 and you get the neutral current. Okay. For the balanced Y connection, of course, if it is balanced, then the sum of IA plus IB plus IC, right? In this case, a balanced Y connection, the sum of IA plus IB plus IC becomes 0, or you still remember your neutral current is 0. Okay, so the neutral current is 0, so that you don't have any zero sequence current. The line current have no zero sequence. Okay. In any three-phase system with no neutral path, such as delta or ungrounded neutral, the line current have no zero sequence component. If you don't have any neutral path, right? For example, the delta, okay, with ungrounded neutral, the line current have no zero sequence component. Okay, because you don't have any neutral. Okay, let us see how we can apply the sequence component. Okay, you can see that for this example, you have VA, VB, VC, VAN, VBN, and VCN. Okay, all these three have the same magnitude, and the angle separation is 120. So this voltage, right, VAN, VBN, VCN is balanced. So this voltage can be, conclude that these are balanced. So if these are balanced, if you want to find the sequence component of this guy, what would you see is that, the zero sequence is 0, right? And V1, okay, which is the magnitude of positive sequence. The magnitude of the positive sequence itself is VAN, okay? The positive sequence itself is VAN. And the sequence component, negative sequence of this guy, okay, of this set is 0. Why is it so? This is a nice transformation. You see that VAN, VBN, if you write in this case, this is VAN is here, and VBN is over here, and VCN. Okay, if you draw from VP, given VP with the length of 277, right? So these three vectors are positive sequence. Once you compute the components of these three vectors, it would say that, the first thing is that you have a zero sequence. You have no zero sequence, which is 0 here. But this would tell you that, this set of phase voltage is balanced, right? The message here is that this, if you have zero sequence, right? You have no zero sequence. I don't want to repeat 200, right? I don't want to say zero sequence, but this is no zero sequence. If you if you don't have uh, zero sequence, okay, it tells you that this is balanced. All right, since the voltage is positive sequence by itself, the VP is positive, so you don't have any negative sequence. This is clear. Okay, so let's just read the explanation that is given here. This example illustrates the fact that balanced three-phase system with ABC sequence or positive sequence have no zero sequence or negative sequence. It doesn't have any negative sequence component, right? Because we gave the positive sequence inputs, we give the positive sequence phase quantities, right? So the return you would get just the positive sequence. For this example, the positive sequence V1 just equal to VAN. So soon after you know the VAN, as we discussed, right? So if you know the VAN, now you just add up with the angle shift of 120, so you get VVN, VCN. Okay. Let's just see in a different form. You see that IA, IB, IC, all these trees are balanced, of course, because of equal magnitude, right? The equal magnitude and the current, I mean the phase displacement is 120. Now you can see that IA is 0, IB is plus 120, so plus 120, IA would be here, and IB is here, right? And IC is here. So now you see This is IA, IB, IC. Everybody knows that this is the negative sequence. Okay, negative sequence. The angle separation is 120 with equal magnitude. So this is balanced negative sequence. If this is balanced negative sequence, so everybody knows that there is no zero sequence. Okay, you put this into the calculation, you see that the I0 is zero. It is zero because this is balance. Okay, this is balance. Now you gave the negative sequence, so your positive sequence is zero. This is zero because the input, right, the phase quantities are negative sequence. So the positive component is zero. Okay, this is zero due to the given phase current negative sequence. Okay, because the given phase sequence are of negative sequence. Now the I2 would return to just IA. Okay, just returns IA. Okay, and you just, it's clear, right? You turn the IA and you just rotate, based on the angles of the negative sequence. Okay, it's clear, right? Now, what happens if we have just, unbalanced currents? If you have unbalanced current in this case, you see, this is unbalanced because, IA is 10, okay, and angle of 0, IB is 0. So now you see that there is no current IB, okay. Probably this is due to the what? The series fault. Okay, you still remember? This might be because of the series fault. You just lose the conductor in phase B, right? So there is no current flows in IB. Okay, so an IC is the same magnitude of 10 and the angle of 120. So the problem asks you to calculate the sequence current and the neutral current. In this case, you must have the neutral current somehow. Okay, you see that if you can manage to find the I0 from the transformation, right? The neutral current IN would be thrice of the three times of the I0. Okay, now you see the I0 can be defined by this, 1/3 of the sum of all currents, right? The 1/3 of IA plus IB plus IC. Okay, the I0 is 3.33 angle of 60. Now you say that the neutral current, you can answer straight away that is 10 angle of 60. You multiply this by 3. Okay, you multiply this by 3 and the positive sequence. Now, since it is unbalanced, okay, it is unbalanced. So there is no way that the I1 and I2 becomes 0. Okay, if it is 0 means that it is balanced. Okay, now you can do your math, the math yourself, right? So the IA is from this formula and you get 6.667 angle of 0, and I2 you get by plugging into the formula, right? 3.33 angle of negative 60. Now you see that since the unbalanced current, you have both positive and the negative sequence, and moreover, you also have the ice, the zero sequence. Okay, because since it is unbalanced, right? The sum of IA, IB, and IC is not zero anymore. So there is not, it is not zero. So there is a neutral current, right? This is a Y connection. Okay, this is clear, right? So if we discuss the power, what would happen to the power in the sequence network? Okay, we just look into the general formula first. If we have the three-phase load, in this case the impedance load, okay, we want to see how much power is being consumed by this load. Okay, we express the three-phase consumption of this three-phase bunch of load by the multiplication. Okay, this is a multiplication between V and conjugate of the phasor current. Sorry, this is the phasor current. Yeah, yes. Okay. The SP standing from this is a three phase, right? Complex power expressed in terms of the phase quantity. Okay, expressed in terms of phase quantities. Okay, so we can see that this is the VAG times I, right? So all these are in complex form. Okay, the sum of all the the phases. Remember, this is unbalanced, right? So we cannot multiply this just by 3, okay, because the different phase has a just different voltage, different angle. So you have to find from the sum of the complex power being consumed by each phase. Okay, now you can re-express this equation by the matrix notation. You can see that this is the matrix notation. Okay, the linear sum of this guy can be expressed in terms of the multiplication between row vectors and a column vector. Okay, you just multiply this, but you have to bear this in mind when we write in a short form. Okay, we normally assume, right, that the row vector is in the normal vector quantity, but if you want to express the row vector, you have to just put the transpose. All right. Now VP and IV, VP transpose times conjugates of IP. Now we just want to see, right? Our goal is that we want to re-express this formula in terms of the sequence quantities. So what do we have to do here is that we know that Vp is A times Vs and Ip is A times Is. So we just put these two relationships in this formula and you get this guy. Okay, you get this line. Now you rearrange this a little bit, right? You just rearrange this because you get A Vs transpose times A times Is conjugate. Okay. Now, since the matrix are in multiplication, you can relocate the matrix. Okay. Now you relocate this to put A transpose with the A conjugate. So you have to see the property of this guy. Okay, A transpose times A conjugate. A transpose times A conjugate. Okay, the people have done this for you already, right? So once you have multiplied these two matrices, what you get is that you get 3 times identity matrix. Okay, 3 times identity. Okay, once you have put this 3 times identity back to the to the original to this equation, you put this back to 3 times identity u. Okay, 3 times u. This is identity matrix. Okay, now you have this equation. Okay, you have this equation. This equation would tells you that SP is equal to 3 times Vs transpose times Is conjugate. Basically, if you see just this term, Vs transpose times Is, this would translate into what? This would translate into S of S, right? S of S standing from for the complex power expressed in terms of sequence quantities, right? Sequence quantity. Okay, so the summary is that the total complex power delivered to the three-phase network, right, equal to the 3 times the total complex power delivered to the sequence network. Okay, this is the conclusion. Okay, if you manage to find the complex power in phase in sequence quantity, if you want to know what should be the complex power in phase quantity, you just multiply this by 3. Now you can see the grace of this equation, right? You have transformed, okay, the unbalanced complex power equation, okay, If you want to just, if you want to analyze, if you want to find the complex power for any unbalanced circuit, right? What you have to do is that you have to analyze phase by phase, and you have to sum up all those complex power. Okay, this is the direct method. Okay, the better method, or the transform method, is that if you manage to know the power being consumed by the sequence component, which is, what, in the sequence network, everything is balanced, right? Once you transform to the sequence network, okay, everything is balanced. So you might just multiply this by 3, then you get the total current, total power. Okay, so this expression is just like, the one that we have made for the balanced three-phase power system. All right. Let us do one example in order to wrap up this, the first clip, right? The power in sequence network is that, if you have the SP, you calculate the SP, which is the complex power in phase quantity, and SS delivered to phase current, three-phase source. In example 8.6, 8.6 is here. Okay, example 8.6 is here. This is 8.6. Okay, verify. The problem asks you to verify that the SP is equal to 3 times SS. Okay, so you can see that this is unbalanced, of course, right? VA, VB, VCs are unbalanced because of the different magnitude, and the angle separation is not 120. Okay, and IA is also, unbalanced because you have 25.15, 25.71. These are unbalanced, and definitely because of unequal magnitude, and the angle separation is not 120. Okay, now if you want to find SP, which means the complex power based on the phase quantity, so you need to use these two lines. Okay, you have to use these two to compute the SP. How to do this one? Because just simple, right? VA IA conjugate, right? VA times IA conjugate. Okay, this one, this guy times this guy conjugate of this guy, and you do the same with the other two phases. Okay, so now you get this equation, you get this one. Okay, you get this VA. Okay, now you analyze this in the sequence domain. Now, in order to achieve this sequence domain, you need to transform the voltage, right? VAG, VBG, VCG to this V0, V1, V2, right? This is what you have achieved, okay? And also, you need to transform IA, IB, and IC in order to have this line, these three lines, okay? Now, soon after you know this one, these two, right? You just multiply this with this conjugate of this, right? V0 times I0 conjugate, this becomes 0, plus V1 times I1 conjugate, okay? V1 times I1 conjugate plus V2 times I2 conjugate. You sum up all these, products, all these three products. Once you have this, right? You have this, okay? Once you have computed this to the sum of these three products, you have this one. You can see that, right? In order to get the total power in the phase quantity, you just multiply this by 3, so you get the same number. Okay, you get the same result. All right. I hope this is clear, right? This is quite clear to you. So I will just stop the first clip, and you will see you in the next clip. That would take you just less than 20 minutes. All right. See you in the next clip.